So we're going to revisit some ideas from the previous lesson on photoelectric effect in today's lesson on stopping potential. So here I have a circuit, and this here is a metal surface, and we have an ammeter connected in series, a voltage connected in parallel, and this is just a normal battery here. One thing that you need to know about this circuit: if this battery is a positive terminal at this end, it means that this terminal here at this point is positive, and if it's negative on this side, this terminal of this metal surface here will be negative. So we can determine the polarity of this receiver here and this metal surface. And we saw from last time that when we have incident photons on this metal surface, electrons are going to get released. So the photons hit the surface, and we're assuming that the energy of the photons is greater than the work function. So we know that the electrons are therefore going to get released. So if we say that these are electrons here on this metal surface that have just been released, when I apply a voltage and this side is positive, we can clearly see that this terminal here is also going to be positive. So if we have a positive terminal on that side, the electrons are clearly going to get attracted to that terminal. So in this scenario here, the electrons will accelerate towards the positive terminal, or the positive side of this receiver, let's call it. So this is quite nice, but it's not really anything interesting. It only becomes interesting when I actually swap the terminals of the battery. If I connect the positive end to the right hand side, this means that this metal surface here is the positive side, and this receiver, let's call it, is the negative side of this terminal. So now once again I have incident photons, where the energy of these photons is greater than the work function. But this time, when the electrons get released, you can see that this side here is a negative side. So they're going to be experiencing a repulsive force. And we know that when these electrons are released, because the photon energy is much greater than the work function, we know that this means that there will therefore be a range of kinetic energies of electrons. So these electrons are going to experience a repulsive force, and therefore when they get released, because of this repulsive force, as they try to move across, their kinetic energy is going to start decreasing. Now, if I decide to increase the voltage, what that means is the repulsive force experienced by the electrons will increase. And if I keep increasing it, I'll get to a point eventually where the repulsive force is so strong that the electrons cannot actually jump across the other side. And this is because, well, we know that work done is equal to the charge times by the voltage. So if we increase the voltage, we're increasing the work that needs to be done against this force in order for the electrons to reach the other side. And what determines if the electron will reach the other side or not is whether this kinetic energy of the electron is greater than the work done or not. If the kinetic energy is greater than the work done required, the electrons will reach the other side. However, if we keep increasing the voltage such that the work done is greater than the kinetic energy, then the electrons cannot reach the other side. So let's use a graph to represent this idea. So let's say I had the intensity of electrons, or the current coming from these electrons, on one axis, and the voltage that we're forcing on the other. Well, we know for positive voltages, the electrons are going to be accelerated from the metal surface to the other side. So there will be some electrons that get just about liberated, but with zero kinetic energy. When you apply this positive attractive voltage, these electrons will get attracted to the other side. Hence, there will be a slight increase in the current that you see when increasing the voltage. But eventually it will start to plateau, because now all the electrons will have reached the other side. And we know that a certain number of electrons can be released because only electrons that have a work function less than the photon energy can be released. However, when we start to swap the terminals of the battery and therefore apply a negative voltage, we can see that the number of electrons that reach the other side starts to decrease. And the reason it starts to decrease is, well, we know that there is a range of kinetic energies. So some electrons have higher kinetic energies than others, which means that for some electrons you need a greater work done or a greater potential on the battery in order to resist it from reaching the other side. And this point here, when we start to see that no electrons can reach the other side, is known as the stopping potential. And the stopping potential is equal to the maximum kinetic energy of the electrons released. So let's look at a slightly different setup now, away from stopping potential. And instead of having a battery, I just have a normal wire and just an ammeter measuring the current. We are told that the work function of this metal surface is 2 electron volts. And once again, I have this photon generator that has a range of frequency values. Now, if I set the frequency of this photon generator such that red colored photons are incident on this surface, well, red light has a long wavelength, and we know that wavelength is inversely proportional to energy, so this red light will have a lower energy. When we set photons with the wavelength of red light onto this metal surface, we will see that no electrons are liberated. However, if I were to use green light or even violet, these colors have a greater frequency and a lower wavelength than red. So what that means is, for green and violet, their wavelength is lower, so therefore the energy of these photons are greater. And in this case, the energy will be greater than the work function. So electrons are liberated with some kinetic energy. Now, what were to happen if I decided to increase the intensity of photons incident on this surface? And what that basically means is, what happens if I increase the number of photons incident on the metal surface? Well, we know that due to the one-to-one relationship between photons and electrons, because there are more photons incident on the metal surface, you're going to see more electrons released. And if you release more electrons, you're going to see a greater current. So the ammeter reading will be larger. However, if I stuck with using the red light, which has an energy less than the work function, if I increase the intensity, what I will see is no change in the number of electrons released. And this is because the energy of this red light is less than the work function. So the photons do not supply the electrons with enough energy to be liberated. So no matter how much photons I hit on that metal surface, because of the one-to-one relationship, no electrons are going to get released. And therefore, no current will be produced. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.